All right, hello everyone. Welcome to another pre-recorded lesson. Today, this video, we start a new unit, compound structure and properties. Now this video will cover the material for topic 1, but in class, we'll cover the material that is covered in topic 2. So one important objective for this unit is to be able to explain the relationship between the type of bond and the properties of the elements that are involved. Okay. And then today we're going to learn that valence electrons and electronegativity will determine the type of bond that is formed. Okay. So chemical bonds, by definition, are the attraction between the nucleus of one atom and the electron of another atom. Okay. And usually the electrons that are involved in chemical bonding are valence electrons. Okay. And we saw earlier electronegativity determine the type of bond that is formed. Okay. So just a little quick review from the previous topic and unit. Electronegativity is an atom's ability to attract electrons to itself. Okay, and the pattern increases going from bottom left to the right. Okay, and this all has to do with energy levels, how far the electrons are away from the nucleus, as well as increasing nuclear charge, how well that nucleus can pull on those electrons. So there are three types of chemical bonds. There's ionic, covalent, and metallic. And we're going to go through the three of these. Ionic bonds we're going to spend probably the least amount because we've dealt with these a lot in our previous chemistry classes. Okay? Ionic bonds occur when electrons between two atoms are transferred. Okay? And this happens between a metal and a nonmetal. Okay? And here I have a simplified visual of the periodic table where there are metals and where there are nonmetals. Okay, do you remember what the elements are called that are in orange? Okay, those are called metalloids or semi-metals. Okay. All right, so covalent bonds, okay, opposite of ionic bonds, are when electrons are shared between two atoms. Okay. There is no transfer, and this usually happens between nonmetals. Now there are some exceptions, as you can see. If you go on to study organometallics, you'll find that there are some metals on the periodic table that will covalently bond with other elements. Okay, ferrocene is one of the first examples. Okay, so here we have an example of two nonmetal hydrogen atoms. The closer they come in contact with one another, the probability of each of those electrons increases between these two nuclei. And the reason for that is due to the octet rule. Okay, both elements are trying to satisfy the octet rule. In this case, 2 electrons. Okay. Now, when two elements of different electronegativity come together, we form a polar bond. Okay, and there are some common notations that you need to be aware of moving forward to designate which part of the bond is more positive and which one is more negative. Okay, so the D with the minus represents the higher electronegativity. That is a partial negative because if you think about it in terms of an ionic bond, that element is pulling the electrons in the covalent bond closer to the nucleus. So it's getting a more negative charge-ish. Okay. Polarity. Okay. A covalent bond is nonpolar when the electrons are equally shared. Okay. And then they are polar when electrons are unequally shared. And that is usually when there is a difference in electronegativity. Okay. Diatomic nitrogen. Okay, has 3 covalent bonds between the two of them. Okay, and even though nitrogen by itself does have some electronegativity, because the opposite is the same element, those poles are canceled. So diatomic nitrogen would be nonpolar. Carbon monoxide, however, also has 3 bonds, but oxygen is more electronegative than carbon, so there is an unequal pull of those electrons that are involved, which means carbon monoxide is polar. Okay? So carbon would have a D plus or partial positive. Oxygen would have a partial negative. Okay? And I don't know if I mentioned this earlier, but one way to designate the direction of the polarity are with these types of arrows, where it's an arrow, but on the left side, or whatever side is the positive end, you have this little positive, the arrow, and then the arrow kind of directs to the more electronegative atom. All right, so answer this question. Consider a phosphorus chloride bond and each of the atoms' electronegativities. Which element has the partial positive? And that would be phosphorus. Okay. The dipole arrow points toward what element? It points toward the more electronegative atom, which in this case is chlorine. Okay. And finally, what type of bond is this? This is a covalent bond, because both phosphorus and chlorine are nonmetals. Between these four types of covalent bonds, which one is most polar? Oops, sorry. It is the carbon fluoride bond, because all of these bonds have one carbon, so you have to look at the other atom to see which one is more electronegative, and that is fluorine. All right, final question. If the electronegativities of fluorine and hydrogen are 4.0 and 2.1, is diatomic fluorine more polar than hydrogen, or diatomic hydrogen? They are both nonpolar, okay, because both elements are involved in the same bond, so they cancel each other out. All right, metallic bonds, okay? As the name implies, metals only, okay? And in this case, there's not really a bond directly between two atoms. The electrons that are involved in metallic bonds are more delocalized. And what that means is they're not really in a fixed space. It's what they call a sea of electrons. So they're kind of floating haphazardly around the individual atoms. So as opposed to valence electrons that are associated with individual atoms and then can thus bond with others, the valence electrons for metals are definitely more mobile. So they're just kind of floating around and interacting with this kind of a plasma type of thing. Okay? But it's not really plasma. All right. Tungsten, okay, is one of the hardest metals on the periodic table. And you would predict, based on that statement, that there are a lot of metallic bonding going on. So there's a lot of sea of electrons. Opposite of tungsten, the softest metal is cesium, also one of the more explosive ones or reactive ones with water. Has very little metallic bonding going on, so it's not a very hard metal. Okay? We like metallic bonds, okay, because they account for malleability, ductility, and conductivity. Okay, gold is what is famous for its malleability. You can take a very small amount of it and plate things with it and really stretch it out and hammer it into different shapes. Okay, ductility, copper is a fantastic example. You can take a lump of copper and just kind of draw it out into these little fine wires. Silver, you can do that too. However, silver is great for conducting electricity as well as thermal conductivity. All right, I think that's it. Thank you for your attention today. We'll see you in class. Thank you.